Hi, this is Tzvi Rosen. In today's commutative algebra lecture, we'll be talking about Spec, which maps a ring to its spectrum. And Spec is a map from the category of rings to the category of topological spaces. So first we'll describe what a topological space is and describe how we can put a topology on the set of prime ideals associated to a ring. Then we'll look at some examples of spectra of rings. And finally, we'll talk about functoriality of this map. That'll require us to talk about what categories are, what functors are. So there'll be a lot of new material today, but hopefully you'll bear with me. And you can find much of this material, though some of it is from other sources, in the exercises to Chapter 1 of A.T.M. McDonald. Those are exercises 15 to 26 is where they talk about Spec. Okay, so we'll start by defining a topological space. So a topological space is a pair, x tau, where x is a set and tau is a collection of subsets of x satisfying the following axioms. First, we say that the empty set and x are both in tau. Okay? And arbitrary intersections in of elements of tau are also in tau. And finally, finite unions of elements of tau are in tau. Okay, so it's important to note that the unions must be finite, but the intersections are allowed to be arbitrary. And under these set of axioms, tau is called the set of closed sets of the topology. Okay, and you can also define a topological space by the open sets of the topology, but then you would swap the intersections and unions. Just to give you a few examples of topological space. So for any set x, if you have, well, I suppose it should be non-empty set. Let's say for any set x not equal to the empty set, you can have trivial topology, where the only closed sets are the empty set and the full set. Okay. And you can check for yourself that all of the axioms there are satisfied. Another topology on the same set would be the discrete topology. And that's where we designate every set to be closed, and that would just be power set of x. Okay. There are also these it's very easy to show that the axioms are satisfied in these cases. Slightly more intuitive, if more difficult to define topology, is called a metric topology. So for, let's say, x equal to Rn, we have the metric topology, also known as the Euclidean topology or the classical topology. Let's call it Euclidean topology. And this has, among its closed sets, so tau equals, or let's put it this way, the closed balls around points are in tau, as well as anything else you want to construct with those closed balls, including unions and intersections, et cetera, et cetera. Okay. So these are a bunch of topological spaces, just to give yourself familiarity with the idea that its topology is not just the Euclidean topology that we're familiar with, but also a whole bunch of other things. And we're going to explore one of those today. So we're going to take a ring R, and we're going to have E be some subset of R. Not necessarily an ideal, just a subset. We're going to define V of E to be the set of prime ideals containing E. Okay. And if we define spec R to be the set of prime ideals of R, and the topology to be given by the set of V of E for E a subset of R, these will be the closed sets, then this defines a topology, a topological space. Okay. So let's verify that that actually satisfies our axioms. So we're claiming that V of E, set of V of E for E contained in R should satisfy the axioms for closed sets. So let's check the first axiom. We need to have the empty set and the whole set to be elements of tau. Let's just call this tau. So we need these to be in the set of closed sets. Well, if we take the empty set, if we take E to be any set containing 1, then obviously no prime, the only ideal containing 1 is the whole ring. We do not consider the whole ring to be prime. Therefore, the set of prime ideals containing 1 is the empty set. On the other hand, if we take X, this would correspond to V of 0, since every ideal has to have 0 in it, because 0 times an element of your ideal needs to be in the ideal. So 0 is there. Okay, great. So we satisfied the first axiom. Next, we need to see that arbitrary intersections are still in the closed sets. Okay, so we're going to say if we have V of EI, where I is in some index set, then so we're going to claim that this intersection is actually equal to V of the sum of the ideals generated by each of the EIs. Okay? Okay, that probably requires some justification, but I'll leave that as an exercise for now. As for finite unions, Well, if we have union of V of EI, so if we take, again, the ideals generated by each of these EI, this is going to be equal to V of the product from I equals 1 to n of the ideal EI. Okay. And this also gives us some intuition as to why the intersections are allowed to be arbitrary, but the unions must be finite, because you could take an arbitrary sum of ideals, right? Because any element is just a sum of finitely many elements from any one of your, or any subcollection of your set of ideals. Whereas a product, you need an element of each ideal, and so if you're multiplying together infinitely many elements, that's not a well-defined thing to do. Another way of approaching this topology is through the basic open sets. So we should observe that open sets are complements of closed sets. And a basis for the open sets is a collection B such that any open set can be expressed as a not necessarily finite union, just as a union of elements of B. And for the topology that we're developing on the primes, the basic open sets, the basis of open sets that we're going to define is the set D of F, for F an element of the ring, and this is going to be the set of primes such that F is not in P. Okay, so it's the set of primes not including F. Okay. Equivalently, this is spec of R set minus V of F. Okay, so if you take all of the primes that do include F and you subtract them from the set of primes of the ring, you're left with D of F, which is sometimes called a distinguished open. Okay. And okay, so now we want to prove that these distinguished opens actually form a topology. So take U subset of spec R open. Okay, and we want to show that this is a union of basis elements, a union of the distinguished opens. So that means that U is equal to spec R minus V of I for I in R. Okay, just by definition of the closed sets. And what this means for us is that for any x in U, so any prime ideal in the set U, we know that it's a prime that does not contain I. So I is not contained in X. Well, if you have that this isn't contained, then there must be something that's in I which is not in X. So this means that there exists Fx such that Fx is an element of I, and Fx is not an element of X. Okay, Well, that means that, so the fact that fx is not in x tells us that x is contained in d of fx, right? Because d of fx is just the set of primes not containing fx, and x is one of those. So x is in d of fx, and the other thing we want to show is that d of fx is contained in u. And the way that we do that is we use this part. So the fact that fx is in I, that indicates that the ideal generated by fx is contained in the ideal I, or the ideal generated by I, depending on if we start out with an ideal or not. But if we think about the set of primes, containing fx and I, well, everything that contains everything that contains I, because fx is in there, must also contain fx. So the set of primes containing I is a subset of primes containing fx. So everything that contains I must contain fx. Okay, so little difficult to trace, but I think we got it. And when we take the complements of each of those, the containment switches, and we get d of fx is contained in the complement of v of I, which, as we defined above, is u. So what that tells us is that u is equal to the union for x and u of d of fx as defined above. Okay? So that tells us that this is a basis for the topology. Okay, so now we've got a sense for this topology on the primes. And this is called the Zariski topology, if I haven't mentioned, named after Oskar Zariski, who was one of the fathers of algebraic geometry. Now that we have a handle on the topology, we can do some examples. So the first example is spec k for k of field. So as we know, the only ideals of a field are the zero ideal and the whole field. But the only one of those which is prime is 0. So so spec of k is just a single point, and the topology is the empty set and the point. Okay, so this is our spec k. This is this is the simplest spec you could have. Now let's consider spec z, where z is the integers. So the set of prime ideals of z are just, that's just the set of principal ideals generated by a prime number, as well as the zero ideal. Okay. And so if you look at any p, so if we want to find v of p, so the set of prime ideals containing a given prime, that's just going to be the prime itself. So each of these points is closed. But if we wanted to look at the set of prime ideals containing 0, well, 0 is in every prime ideal. So this is going to be the set of prime. This is really just going to be all of spec z. Okay, in particular, 0 is not a closed point. Okay. How about other closed sets? Well, we need some element of the ring, and we want to consider all of the prime ideals that contain it. So some element of the ring of integers is just an integer, and the set of primes that contain this is P such that P divides N. So this is going to be a finite collection of primes. So if I wanted to draw a picture of spec Z, I would draw a point, a closed point for each prime number. And I could draw kind of a fuzzy point for 0. Because when you choose 0, you get the whole line, including all of the primes. Okay? That's the closure of the prime ideal 0 in this topology. Okay, and finite collections of points, of closed points, gives you closed sets. Okay, now let's look at spec of polynomials with complex coefficients in one variable. So the fundamental theorem of algebra tells us that every polynomial over C factors into linear polynomials. So the primes of C of spec C of x is going to be the set of linear polynomials, or ideals generated by linear polynomials, x minus a, where a is a complex number, as well as, of course, our 0 ideal. Okay. Well, what are the closed points here? So just as before with the primes, the set of prime ideals containing x minus a, the set of prime ideals in this ring contain, or in this spec, for any given linear polynomial, so v of x minus a, this will be just the prime ideal generated by x minus a, so this is considered a closed point, whereas v of 0 will once again be the whole spec. So this is not closed. And if we want to think about just an arbitrary polynomial, what's the closed set corresponding to that? Well, this is just going to be the set of polynomials generated by x minus a, where a is a root of p of x. Another way of writing that, p of a equals 0. Okay, and if we want to draw a cartoon of this, similar to the cartoon of the integers, we have a line, and we have all of our complex numbers on this line, so x minus 0, and x minus 1, and x minus I, and x minus the square root of 3i, and x minus pi plus I, etc. And then we also have this fuzzy 0 point, which is not closed. Okay, and closed sets are same as before, finite collections of closed points. Okay, how about spec C adjoin xy? So here, things start to get a little more complicated. So what are the prime ideals here? So we have certainly, if we take ideals of the form, well, we always have the 0 ideal, right? In an integral domain, the 0 ideal is always prime. So that's one. And we also have the maximal ideals. And if you think about what would be a maximal ideal here, So you would want to consider a map you would want to consider an ideal so that it's the kernel of some homomorphism to the ground field. And so the evaluation map would be good for that. So you can take just x minus a, y minus b, where a and b are both elements of complex numbers. What else do you get? Well, here you get the set of prime ideals generated by irreducible polynomials in x and y. And I guess you can add over C. Okay, and here you get all sorts of examples. You can get your circles and your cubic curves. Et cetera, et cetera, et cetera. And if we want to think about which of these points are closed, so these ideals are maximal. Right? When you quotient by these, you get a field. And so the set of prime ideals containing them, well, the only ideal containing a maximal ideal besides the whole ring is itself. So that means that these are our closed points. So the maximal ideals correspond to closed points. If we think about the set of prime ideals containing 0, so that's all primes, right? 0 is in every prime ideal. So this is, you can think about that as kind of a generic point for the whole C2. Right, because every prime ideal is going to be in the closure of this point. As for the irreducible polynomials, so if you take just the ideal generated by f irreducible, so this is going to describe a non-empty, assuming this is a non-constant polynomial, it's a non-empty set of points where f evaluates to 0. Okay, so the closure will include all ideals x minus a, y minus b, such that f of ab equals 0. Okay, so these also are not, these points are not closed. The only closed points are the maximal ideals. But you can think about the points generated by a single irreducible polynomial as kind of generic points for these what we call algebraic varieties, these shapes corresponding to solution sets of the polynomial. So for instance, so we have our C2 here. Obviously, this looks like C1 because C is determined by 2 real dimensions, but imagine this is C2. So you have this kind of messy, generic 0 point living here, which when you take the closure, you get the whole space. And then you have closed points corresponding to maximal ideals. For instance. But then you also have these subvarieties, these solution sets to irreducible polynomials. So this corresponds to x squared plus y squared minus 1. And then when you take the closure of that, you get all of the individual points inside here. So for instance, this maximal point, this maximal ideal corresponding to the point 1, 0. So we'll say it's x minus 1, y. That's going to be in the closure of x squared plus y squared minus 1, as well as all of the other maximal ideals correspond to points in that solution set. OK, so that's spec cxy. Now let's look at spec of Rx. So this is going to be similar to spec of Cx. The prime ideals here, so you, as before, you get your 0 ideal. You also get things of the form x minus a for a and r. But then you also get these degree 2 polynomials, x squared plus ax plus b, where this is irreducible. Okay, in other words, this satisfies, oh no, the letters are off. So this is going to be a squared minus 4b is negative. Okay. Okay, and so these are the set of prime ideals. So you could picture this as being kind of normal maximal ideals associated to real points. You have x plus 1, x minus 3.1. Let's just make it pi. X minus pi. Then you also get these kind of pairs of complex conjugate points. So corresponding to, for instance, x squared plus 1, or x squared plus 2x plus 4. And these are actually also closed points because they're maximal ideals. There's no prime ideal containing this in R join X. So this is our fuzzy 0 point. So 0 is not closed, but the others are. A category C is given by a pair the objects of C and the morphisms of C, where these satisfy certain properties. So satisfying, so first of all, every morphism is between two objects. So F in the morphisms has a domain and a codomain. In the set of objects. In other words, F maps A to B, and A and B are objects in the category. Okay, if you have some F which maps A to B, and some G which maps B to C, then there's this then there is a composition G performed after F, which is contained in the morphisms from A to C. So you have to be able to compose maps as long as their codomain and domain are appropriately matching. Okay, and you also need associativity of composition. Okay, so if you have maps where these compositions make sense, you've got H of G of F, so you need to be able to do these first or these first and get the same thing. And you also need to have identity. So for every object in the category, there's a map in the morphisms of X to X called the identity. Okay. And this identity map has to play nicely with other morphisms. So if you have F post-composed with the identity, that's going to be equal to F. And similarly, if you have G pre-composed with the identity, that's going to be equal to G. Okay? So assuming all of these have the correct domains and codomains. Okay, so if you take all of these things, that defines a category. And I know it's pretty abstract the way I described it, but the main thing to keep in mind is that you have objects and you have morphisms, which you can think about as maps or arrows, which tell you how to go from one object to another. Okay, and let's actually give a few examples of categories. So one example is sets. Okay, and the category is usually called set. And this has objects given by sets, and it has morphisms given by set maps. Okay, pretty straightforward. Another category is group, and the objects here are groups, and the morphisms are group homomorphisms. Another example is ring. Kind of getting the hang of this by now, hopefully, is that the objects will be rings and the morphisms will be ring homomorphisms. Okay. You can also have top. And the objects here will be topological spaces. And the morphisms will be continuous maps. And we haven't spoken about that yet, but continuous maps are satisfied that the preimage of an open set is open. Preimage of open is open. So these are the morphisms that we choose for the category of topological spaces. Okay. So now that we have these categories, we want to have a formal way to compare them. And the way that we've developed to do that is called a functor. We say a map F from category C to category D is a functor if you have a map first of all, from objects of C to objects of D. Okay. That's first. Okay, so for any pair of objects, x and y, in C, okay, you're going to need, so once you map through to the next category, you want all of the morphisms between those two objects to also map through. So there's a map from morphisms of xy to morphisms of f of x to f of y. Okay, and we've defined that map of objects in the previous line. And this has to satisfy the following. This has to first take the identity map to the identity map on the new object, and it has to take the composition of two maps to the composition of the corresponding morphisms in the target category. Okay, so it respects both the identity and the composition. Okay, so but the fact that the order here stayed the same, so the f is happening after g, even though you write g to the right. G happens first and then f. So this is a covariant functor. And there's another version, so a contravariant functor. Sends f from morphisms from x to y, that goes to morphisms from f of y to f of x. And the composition that needs to be satisfied, so obviously, so the identity stays the same, but f of f composed with g is going to be equal to f of g composed with f of f. So the f and the g switch orders under a contravariant functor. Okay. And now let's look at a few examples of functors. So the simplest functor is the forgetful functor. And this sends categories to less complicated categories. So, or basically categories with less structure. So you can send group to set by just forgetting that every object has a group structure and just thinking about all of the homomorphisms as functions on sets. So treat each group as a set. Similarly, you can map a ring to group, and you just look at the additive group structure of the ring. Because every ring homomorphism is also a group homomorphism on the additive group. A second example, which is a little less trivial, is the fundamental group. If you look at the category of pointed topological spaces, you can consider this a functor to the category of groups. And you need a point here because the fundamental group is defined given a base point, and it's basically the group of loops based at that point with concatenation of loops as the group operation. And this is a functor because if you take any continuous map between pointed topological spaces here, so that's a continuous map which also sends the chosen point to the chosen point in the target space. So a continuous map gets mapped to a group homomorphism on the fundamental groups. So this is also a functor. Okay. All of this leads us to the grand conclusion that Spec, taking the spectrum of a ring, is a functor from the category of rings to the category of topological spaces. And in particular, we want to look at morphisms and see how this functor acts on morphisms. So the morphisms in ring are the ring homomorphisms, obviously. So we have F from R to S is a ring homomorphism. When we apply Spec, we get a map which we'll call phi F from Spec S to Spec R, which takes any prime in S and it maps it to the preimage under F of P prime. So the reason this works, obviously, is because the preimage of a prime ideal under a ring homomorphism is always prime. And so we want to claim that this is a continuous map. So first of all, we should note that this is contravariant because we start out mapping R to S, and then we end up mapping Spec S to Spec R. And we want to claim that this is continuous, which would give us a morphism in the category of topological spaces. If we look at the distinguished open corresponding to X, so this is the set of P in Spec R such that X is not in P, the preimage under phi F of this map is going to be D of F of X. Obviously, another basic open set, and this is just the set of primes in Spec S not containing F of X. Okay? Because you can recall F maps R to S. Okay, and the fact that the preimage of an open set is open is enough to tell us that this is a continuous map. So we've seen a lot about Spec. We've learned what topological spaces. We've learned what a category is. I think that's quite enough for today. All right, thanks for your attention.